When we talk about chemical processes, we talk about reaction equations. And when we do that, we write them as reactants, in other words, beginning substances in an arrow, and products or ending substances. So here's an example of a reaction equation, and I want to point out a few parts of it. First of all, there are these subscripts. And the subscripts are basically telling you what the bonding is in the molecule. So they give you an idea of molecular bonding. In other words, with NO2, you have one nitrogen and two oxygens in this molecule. Okay, and then you have these numbers out in front, which are the coefficients. And those are basically there to assure that you have a conservation of mass. So when you start with N2O5 and produce NO2 and O2, you need to have the same number of oxygen atoms before reaction as you do after, and the same number of nitrogen atoms before and after. So that's what the coefficients are. They are to assure a conservation of mass, and they are usually going to be whole numbers. You do occasionally see fractions, but usually whole numbers, and we use them to balance the equation. Okay, and then one more thing that shows up on the reaction equation are these letters in parentheses, and those tell you the states of matter. So when you have an S, that means it's in a solid form. An L is liquid. G is a gas. And then we also have AQ, which stands for aqueous, which means a solution in water. So it's an aqueous, so it's something dissolved in water. Okay, and when we want to balance reactions, we have to put in the coefficients. Okay, so we start with some equation that's not balanced, and we start with the most complex molecule generally, use whole number coefficients, and if you end up with larger than the smallest ones, reduce them to the smallest. And remember that you can't change the subscripts because that tells the bonding. We're not changing what the molecules are when we balance, we're just making sure there's a balance of atoms before and after. Okay, so most complex. Two molecules are about the same in complexity. We'll start here. We have arsenic. We have 4 arsenics and 6 sulfurs in this molecule or compound. So we want to balance the arsenics, and we do that with 4 over here, so it's already balanced. Then we look at sulfur. There are 6 of those. We need to have 6 on the other side of the arrow, and there's only 1 here, so we're going to put a 6 out in front, which tells me we now have 6 sulfur dioxides to balance the sulfurs. Okay, so we have sulfurs balanced, arsenics balanced. The only thing left is oxygen. On this side of the equation, we have 6 oxygens here, and 6 times 2, 12 oxygens here, because the 6 applies to the whole molecule. So we have 12 and 6, we have 18 oxygens over here, so we need to have 18 over here, and since there's already a 2, that gives us a 9. Okay, now you try balancing this next equation. Again, you should start with the most complex species, which is this one, and work your way out. 3 irons, so you need to put a 3 in front of this iron, because there's 3 in the product side. So you need 3 in the reactant side. Then in order to balance the oxygens, you need 4. You have 4 here, you need 4 over here, so you put a 4 in front. And then you now have 8 hydrogens, so you're going to need to have 8 over here, which means another 4. Okay, and we will need to, in order to use reaction equations, we're going to need to use molar masses for a compound. So let's do it with the example just shown, Fe3O4. The molar mass is going to be, find out the molar mass for iron, which is on the periodic table, 55.847 grams per mole. And since there's 3 of them in the molecule, we multiply it by 3, which is 167.541 grams per mole. For oxygen, the individual atomic mass is 15.999 grams per mole, and we have 4 of them, so multiply it by 4, and we get 63.996 grams per mole. So we sum those up, and the molar mass for Fe3O4, which is actually iron 2,3 oxide, is 231.537 grams per mole of compound. All right, and that molar mass can be used as a conversion factor between moles and grams, because the units are grams per mole. So it can be used to convert from moles to grams or from grams to moles. Okay, so let's do an example of each. Let's convert from moles to grams. 1.21 moles of iron 2,3 oxide to grams. All right, to do that, we start with the number we have, 1.21 moles. Use the conversion factor so that moles are on the bottom, and that would be 231.537 grams over 1 mole. And do the multiplication, you should get 280 grams of iron 2,3 oxide. All right, let's practice converting backwards. Let's say we have some amount in grams. We'll say 14.77 grams of iron 2,3 oxide. And so we will start with the number we're given, 14.77 grams. Multiply that by the molar mass upside down so that you get grams on the bottom. 231.537 grams per 1 mole. And you will get 0.06379 moles of iron 2,3 oxide. All right, so now you practice. You will need to do this conversion from 26.4 grams of carbon dioxide to moles, you'll need to first calculate the molar mass. All right, start with the number you're given, 26.4 grams, and calculate the molar mass of carbon dioxide. You'll need to use it upside down, and it is 44.01 grams per 1 mole. So multiply, and you should get 0.600 moles of carbon dioxide. All right, so back to our reaction equation. A reaction equation has coefficients, which we used to balance it, and those coefficients are actually the amounts in moles for each compound. And whenever there's not a coefficient listed, it's assumed that it is 1. It's equal to 1. All right, so what is this equation in words? Let's write that out. Iron reacts with water to form iron, and here it is, 2,3. This is an unusual iron oxide, and then it has 2 different states of iron in it. Anyway, it forms iron 2,3 oxide and hydrogen gas. So sometimes you will need to put a word reaction into a formula reaction. All right, and one thing I wanted to point out here is that hydrogen gas means H2. There are some elements that are naturally occurring as molecules. And there are some you should definitely know. Hydrogen is one. So when we say hydrogen, we mean, if we're talking about its gaseous form, it means H2. N2, O2, all of the halides are all diatomic. And then there are some other species that are other than diatomic, like sulfur. So you need to know that when we say these elements, we mean the diatomic form for all of these other ones. Okay, so using that reaction equation above, let's make it so we can see it all at once. Let's talk about how many moles of this product, iron 2,3 oxide, are produced from a certain amount. Remember, there's the mole ratios. If you have 3 moles of iron, how much iron oxide? Well, 3 is in front of the iron already, so if it's 3 to 1, that means if you start with 3 moles of iron, you're going to get 1 mole of iron oxide. So you get 1 mole. And what if you start with 6? Okay, well the ratio is 3 to 1, so 6 is twice as much of this, so you're going to get twice as much of the product. So you would get 2 moles. And what if you started with only 1 mole of iron? Okay, that's a third of this, so you would get a third of this in moles. Okay, when you answer those kinds of questions, you are really doing a conversion in your head, which is easy with these numbers I just gave you, 3, 6, and 1, but for any other number, you need to understand what the process is. So let's do it for 11.2 moles, and here is the process. You take your 11.2 moles of iron, and you multiply by the ratio of what you want to get, 1 mole of iron oxide per 3 moles of iron. That way your moles of iron will cancel, and you'll end up with moles of your product, 3.73 moles of iron 3 oxide. Iron 2,3 oxide. Okay, so that is the process. You multiply by the mole ratio of what you want, number of moles of what you want, divided by what you already have. Okay, so that was all some background information so that you can use balanced equations to calculate in amounts of products even when it's not in moles. Okay, so what is the basic plan? First, in order to use a balanced equation, always convert the amounts to moles, because the amounts are in mole ratios. They're not gram ratios, they're not concentration ratios, they are mole ratios. Then, once you have them in moles, use the coefficients in your balanced equation to convert to moles of what you want, like we just did for iron oxide. Finally, convert the moles of what you want to whatever units you want, grams, molarity, whatever it is. Okay, so let's use the same example reaction and solve a problem. How many grams of iron oxide are produced from 111.7 grams of iron? Okay, so we can set up a big long conversion problem. Start with what you're given, 111.7. I'm going to make this larger again. 111.70 grams of iron. Put it over 1. Okay, the first step is to convert amounts to moles. Okay, this is in grams. To convert to moles, we need to have the molar mass of iron. 55.845 grams of iron. Okay, so that converted to moles. We have grams that'll cancel. So that is step 1 above. Then, step 2 is use the coefficients to find moles of what you want. We want iron oxide, so that is 1 mole of iron oxide per 3 moles of iron. So that is step 2. Finally, convert the moles of your desired substance, the oxide, to whatever units you want. Well, the equation says how many grams are formed. So now we want to convert that back to grams of of iron oxide. And that was 231.54 grams of iron oxide per 1 mole. Okay, if you cancel all the units and do the multiplication, you'll get 154.38 grams of iron oxide. And that was step 3. Okay, now time for you to try. Here's a reaction of nitrogen and oxygen compounds. So try the first problem, then try the second problem. The first one is in moles, the second one is in grams. The first one is more simple. So try them and be sure to stop and work the problem. Okay, so 47 grams of NO react, and we want to know how much N2O is formed. So we'll start with what we have. 47 grams of NO, and convert it to moles. All right, and then we use the mole ratio to figure out how many, and we have not yet balanced this reaction, so we need to do that. Okay, so we need to balance the reaction, and you've got 3 nitrogens on this side and 3 oxygens on this side, so we're going to need to put a 3 in front. All right, so now we can do our next term, which is converting using the mole ratio, 1 mole of N2O per 3 moles of NO. And that will give you moles of product, 0.522 moles of N2O, and that's the question. All right, and now the second part, we want to know how many grams of N2O are formed, and further, we want to know how many grams of the other product are formed. Okay, so we already have moles of N2O, so we can start there. We don't have to redo everything we just did to get moles. Oops. So start with that, 0.522 moles of N2O, and multiply by its molar mass, 44.01 grams N2O per mole, and you'll get 23.0 grams N2O are formed. All right, but what about NO2? Well, the mole ratio of N2O and NO2 are the same. They're both coefficients of 1. So however many moles of this we formed, we form the same number of this each time 3 NOs react. Okay, each time 3 react, we get 1 of this and 1 of this. So the number of moles of N2O is actually going to be the same as the number of NO2s. So we don't have to backtrack. We can start there and say we got 0.522 moles of NO2 as well. But since the number of grams per mole is different for NO2, the answer is not going to be the same. The molar mass of NO2 is 46.01 grams. So we're actually going to get more mass of NO2, even though we got the same number of moles.